Hi, good morning, good afternoon, and good evening to those of you who are joining us today from over 50 countries around the world, and welcome to the Differential Pressure Flowmeter Calibration webinar. I am Katie Turner. I will be one of your hosts today. I am a marketing manager with Beamex, and along with me I have Ms. Sarah Kinnan, Client Services Manager with Beamex, and Mrs. Michaela Cooper, ISA Coordinator for Corporate and Foundation Partnerships, and we will be your hosts for today. Before the presentation begins, I'd just like to go over a couple unique things with you. We will be using video during today's webinar, as you can see, so you will be able to see all of our presenters' faces and actually put a face with a name. We want this to be very interactive. We don't want to be talking at you the entire time. We'd like to engage in a conversation. So there will be 2 question and answer sessions today. One will be about halfway through and the other at the end. We will only allow questions to be typed into the question and answer box. So unfortunately, because of the large audience, you do not have the ability to raise your hand and ask a question verbally. Please direct those questions to Michaela or Sarah, and Sarah will actually be moderating the question and answer session. There will also be several live polls, and when the poll comes up on your screen, we will direct you on how to fill that out. And finally, we want to know what you guys want to see next. We're really excited that there was so much interest in this particular topic, and we'd like to know what you'd like to see in the future. So please take the webinar survey that will appear at the end. And with that, I'd like to welcome Sarah to introduce our speakers for today.
Welcome and thank you, Katie. First off, today I have the pleasure of introducing David Spitzer, Principal at Spitzer & Boys. David has over 40 years of experience in various aspects of instrumentation, process control, electrical, and utility engineering. He's the recipient of many industry awards for his contributions to the process control industry. He is the author of numerous articles and textbooks, including Industrial Flow Measurement, published by ISA. And if all that didn't keep him busy enough, he is a member of the ASME Measurement of Fluid Flow and Closed Conduit Standards Committees, and serves on the editorial advisory boards of Intech and Flow Control magazines. We are very lucky to have you here with us today, David. Thank you for your time. Next up, the technical director who has been promoting calibration management and helping to develop best practices for calibration with Beamex for over 20 years, our very own Ned Espy. He is a consistent editorial contributor to leading industry publications and has received significant recognition from the automation industry. Today, Ned teaches calibration best practices and provides technical support to end users and the Beamex team in North America, creating safer and more efficient processes, one support call at a time. You might have seen this next guy on YouTube, and if you haven't, you're missing out. Who else but the Roy Tomolino, who has been teaching calibration management for 14 years. Throughout his career, he has taught on 4 different continents to people from over 40 different countries. His previous roles include technical marketing engineer and worldwide trainer for Hewlett-Packard, as well as application engineer with Honeywell. So don't worry if you're missing him today. You're sure to see him at your nearest airport, as he is responsible for all Beamex trainings in North America. And if you want to catch Roy live and in the flesh, you can do so this August. Katie, can you tell us a little bit more about that?
Absolutely, Sarah. All right, real quick before we begin, on August 18th, in Houston, Texas, at the Houston Space Center, we will be co-hosting a Best Calibration Practices Interactive Workshop event with ISA. And what do you get if you attend this one-day conference? You get access to all the presentations. Roy and Ned will be there, so combined with their experience along with the other presenters, we'll have over 100 years of calibration experience in one room. So that's pretty exciting. You also get breakfast and lunch, an exhibit to the Space Center, and we will have a networking reception at Topgolf following the conference, which should be a lot of fun. So we hope to see you all there. And with that, I will hand it over to Mr. David Spitzer to begin today's presentation.
Hi there. Excuse me. Hi there. I hope that everyone's doing fine today. Let me just get down to the next slide. But what I want to do first is just go over what we're going to talk about to give you an idea of what's going on and where we're going with this. I'm going to talk for a while about flow measurement. And in particular...
Katie, it looks like we've lost the PowerPoint. There we go.
No, I've got it now. Okay. So anyway, I'm going to talk about flow measurement and some flow meters. But I'm going to want to focus on particular aspects of it that you're going to find are going to be common to different types of flow meters. And then from there, I want to focus on differential pressure flow measurement and talk specifically about issues concerning that. And then Roy and Ned are going to be talking about some of the finer points, if you will, about calibrating and what's going on there. Then there'll be a question and answer session. Afterwards, Roy and Ned are going to talk about calibration of these instruments, and then I'm going to kind of summarize it at the end to talk about flow measurement system calibration. You'll hear the terminology during this system calibration. And just to keep you a little bit tuned in, there are a couple real good slides of things that are happening or that happened inside pipes that I have in that last section, and then we'll have a conclusion and a question and answer session. So moving along here, there are different types of flow meters that are out there, and these are some of the ones that are used in industry. And I've listed them in alphabetical order, and you can read them. I'll read them quickly, but differential pressure, magnetic, mass, positive displacement, thermal, turbine, ultrasonic, variable area, vortex shedding, insertion. In other words, there are a lot of them. Not all of them are used extensively in industry, but I'm going to talk about some of them. And because we want to focus on differential pressure, I'm actually going to do them in reverse alphabetical order, not showing any preferences to any particular technology. Starting at the bottom there, vortex shedding. Vortex shedding flow meters are kind of like the flagpole when you see the flag waving in the breeze, where the wind blows across the flagpole. It causes vortices to be formed. And you can see here you have flow down here. In this particular case, this is your pipe. This is a bluff body that's in the middle of the pipe. And these are the vortices that are formed downstream. Another analogy in the real world is rivers. You might see rocks in a river, and you might see vortices happening downstream of the rocks. In a flow meter, if you double the flow through, you actually double the number of vortices that are formed. So it's a linear type of flow meter. But here's the important thing, and I apologize, I'm going to say this once, I'll say it a few times, to try to get the point across. And that is that you're not just looking at the flow meter itself, in other words, what fits between the two flanges, but the flow measurement system is actually comprised of the upstream piping up here, the flow meter itself, electronics that hang on the side of it, and also the downstream piping as well. So, just looking at one part of it really doesn't do justice to the flow meter. And you're going to see this on other flow meters as I go through them as well. So that's one type of flow meter. Another type is ultrasonic. And by the way, there are variations on the vortex flow meter in a number of ways. There are variations on ultrasonic. There are variations on the other ones I'm going to talk about. And I'm not going into those at this particular time. But this shows excuse me, this shows a transit time ultrasonic flow meter. And if there's no flow in the pipe, you have an ultrasonic signal that's being sent downstream by this line over here. It's received on the other side. You figure out how much time it takes to go from one to the other. And then another signal gets sent up here, another ultrasonic pulse or whatever gets sent the other way. And you can figure out and measure what time it takes to get there. If there's no flow, those times should be the same. And the flow will be zero. Now, if there is flow, what's going to happen is this particular signal here that I show upstream, this particular signal here will tend to be helped by the flow and get there faster. The one that's on the downstream side here shown on the diagram will actually tend to slow down a little bit and get there a little bit slower, so you get a time difference. And the electronics go and they do what they do to come out with what the flow measurement is or what the velocity measurement is in the pipe. Again, I'm repeating here again what I said last time. We have to deal with the upstream straight run that's going on up over here. We have to deal with the flow meter itself and the electronics. And we have to deal with the downstream straight run. And all those things, all of them, can affect the measurement. Moving along to a turbine flow meter, here what we have is essentially, I call it a rotor, but it's like a pinwheel in the breeze. you know, like a little child's toy or something like that, but this is, of course, more rugged for industry. The flow comes downstream, and it basically hits these blades, and the blades, because they're twisted a little bit, they cause the rotor to rotate. A sensor or sensor and transmitter determine how fast the rotation is going on and determines what the flow rate is. This is a linear flow meter, and in the case where you get double the flow, you get twice as many rotations of the rotor. So relatively straightforward. But again, you have to deal with the upstream straight run, the meter itself, the electronics, and then the downstream. And I offer you this, you know, if you think that's not an issue, imagine if you had swirl coming into this flow meter. For example, if you have two elbows that are close coupled and out of plane with one another, you'll create swirl. And if you had a swirl coming in and you've got this rotor that's turning, if the rotor's turning in the direction of swirl, it wants to turn faster. If it's turning in the other direction, it wants to go slower. So you can see how that type of disturbance would tend to affect this particular type of meter. It's just one example. Another type of meter commonly used is a Coriolis mass flow meter. Here the mass, again, it's a mass flow meter, so it's measuring the mass. It's not shown here, but the flow actually, in most of these meters, it splits into two tubes, goes around the tube here, and then back out the other side, and then up and out of the meter. In this case, the tubes vibrate, and because of the mass moving away from the center of vibration, you actually get an acceleration. The acceleration and the force that's associated with it is in one direction on this side, it's in another direction on that side, and the tube will actually twist. There's a little experiment you can do in your backyard with a garden hose and essentially do the same thing, just hanging it down in a U shape and actually swinging it back and forth and then turning on the water. You'll see the twist very strongly, okay, on that. So just something you can do. Now, this particular meter is a mass flow meter, and it splits the flow. And it really is kind of insensitive. It's not that sensitive to what happens on the upstream and the downstream. However, if you have jetting or something like that up here where more flow goes through one tube than the other tube, that probably can cause a problem, okay? And it may be an issue, and you know, if it's really extensive, maybe it causes the meter not to even function. So, you know, you still have the issues, just not as much as the other ones that I mentioned. Moving along here, magnetic flow meters. This shows a magnetic flow meter diagrammatically where you have a insulating and non-conductive liner over here and a magnetic field that's being put across the flow. The liquid has to be conductive, and by pushing the flow through the magnetic field, you actually create a small micro voltage at these two electrodes over here, which is then determined. From that you can determine what the flow is. This is a linear type of flow meter. You double the flow, you get twice as many microvolts across the electrode. Now, one thing I want to mention, because it's a practical consideration that you may see in these diagrams, you see the electrode that's shown on the top and shown on the bottom. If you're actually installing a meter, you don't do that. You know, why not? Well, if you install it on the bottom, it can pick up dirt and things like that, which, you know, that's not good. And if you install it on the top, there could be an air bubble or some gas bubble up on the top and cause you to lose your circuit and not get a good reading. So if you were really doing this, the electrodes would be in the horizontal plane so that you didn't have any of those issues. But again, these are diagrams, and you can't really show it the way it really should be and explain it properly. So now we get back up to differential pressure flow measurements. And in this case, what we have is we have a restriction in the line. Now, I show an orifice plate. The next slides are going to show some other geometries, but basically they're very similar. In the orifice plate, what you have is a plate that fits between two flanges, and it has a hole in it. And the flow comes in, goes through the hole, comes out the other side. Because this is a restriction, and because the velocity has gotten very high here inside the or at the plate, you end up with areas of low pressure and higher pressure through the system. Here are the pressure tabs, and again, they would normally not be on the top of the pipe unless it's a gas flow. But here are the pressure tabs that show the pressure upstream and the pressure downstream. And what we do is, by looking at that differential pressure across the orifice plate, you can determine what the flow rate is. Again, same thing. I apologize for being repetitious. You have to deal with the upstream piping. You have to deal with the downstream piping. And then you've got the orifice plate itself here, the installation, and also the tubing that's not shown here going to the transmitter. That has to be set up properly as well. So a lot of things. These are flow measurement systems, not just flow meters, flow element, flow transmitter. Okay, it's really a system. This is a different geometry called a venturi. It's normally would be smooth here, but my drawing skills are kind of limited. Here you see the upstream pressure, and the throat over here is the downstream pressure. So that's the differential pressure you're looking at. And these type of meters are generally have a lower pressure differential across them than the orifice plate that you saw before, which was kind of a real sharp cut of the flow. This is more of a smoother transition in and a smoother transition out. To give you an idea of why you might do this, it takes energy. Pressure drop is energy in a lot of applications. And there was one project I was working on some time ago where we had a 180-inch venturi, which I don't know how many thousands of horsepower. We were actually pushing the water through that venturi and taking a large pressure drop such as would be with an orifice plate was just, out of the question. You just, you couldn't do it. You couldn't afford to operate. It would be very expensive. So this gives you an idea of a venturi. Let's see here, moving right along. Kind of a, I'm going to say poor man's venturi in a way, is a flow nozzle. And what this is basically a curve that you see here. It goes all the way around the pipe. You can kind of think of it as an orifice plate where the hole is kind of, bent, if you will. And the flow comes in and it makes its way across here. It has a higher pressure drop than a venturi, but a much lower pressure drop than an orifice plate. And this is oftentimes used in steam service. And again, you have to deal with the upstream straight run, the downstream straight run, and also the condition of the nozzle. Just as a side point, some years ago I was involved with a legal case that involved some nozzles, and I was not able to actually look at the nozzle itself, the internals. And that posed, why not? Well, it was in steam service at 800 degrees, 800 psi and 800 degrees Fahrenheit, and it had not been taken out in something like 45 or 50 years. Nobody had looked at it. And the transmitters were not that much better off. They had not been calibrated in 7 years because they had mercury in them and nobody would touch them anymore. So I had to actually take a look at this and prove and show, with logic and reason and science, that these meters were actually functioning correctly. So there were other techniques that I used to do that. But, you get an idea of things that you have to consider. This is another shape. It's actually a trademark of, it's a D-cone, which is from the chronometer. And here you've got the flow coming in. There's your upstream tap. And the flow goes around this triangular piece there. It's hollow in the middle, but it's to the flow stream. It sees it as a triangle. And the flow goes through this annular area here. And then the pressure drop is from here over to the upstream tap. So these are just different geometries. There are others as well and variations on these. So there's quite a lot to it if you so desire. Now, that being said, some of the common threads that I've gone through here are that you really, when you measure flow, you're really looking at a flow measurement system, not a flow element, not a flow transmitter, not some piping. You're looking at everything, the whole thing, in order to be accurate. So here what you have is you have the upstream straight run that you have to deal with, the flow meter element itself, or this plate or whatever you're using, the differential pressure transmitter, which we're going to talk about more today. Ned and Roy are going to talk about that, and also the downstream straight run. And here's key, is all the components must be considered to ensure accuracy. I want to just add a little side note. I mentioned that 180-inch venturi. In that particular installation, a tie-in was made with a bypass line. Now catch this now, upstream of the upstream diameter, of the upstream straight run, I'm sorry. So upstream of the upstream straight run. It was really kind of far away. But when they turned that bypass on, it affected the flow measurement by 10%. Even though we had not played with the upstream straight run and there was some piping between where the tie-in was and the upstream straight run, it still affected the flow measurement by 10%. And it was well documented that that was the case. So with that, I believe it's, let's see, one more slide here. What I wanted to say with differential pressure flow measurement, the flow rate is proportional to the square root of the differential pressure produced. Now, what I do is I just memorize one thing in order to remember that. Is I remember double the flow, 4 times the differential. And so if you have double the flow, 4 times the differential, triple the flow, 9 times differential, half the flow, 1/4 the differential. So, 1/3 of the flow, 1/9 the differential. 1/10 of the flow, 10% flow, 1/100th of the differential. And Ned is going to talk some more about some issues that are concerned with that particular aspect of it. So what I want you to do here is we have a little survey question here. Where do you take the square root extraction? Do you take it in the transmitter, the DCS, the PLC, or both of them? Not sure. And these, no one's looking over your shoulder to see the answers. There is no really right answer. There certainly is a wrong answer. And the wrong answer is if you do it both at the transmitter and in the DCS or your PLC, because then you're not taking the square root, you're taking the fourth root essentially of this, the square root twice. So what I'd like to do is for just on all the questions, I want you to put down what you do. And I see the results here. You can also. You see about half of you do it in the transmitter only, half of you do it in the DCS or PLC. And these two are pretty much, you can make arguments for either one. Neither one is incorrect. Okay, they're both correct. But when you do it in both of them, that's about 20% of people. I guess this follows the 80-20 rule. If you do it in both of them, that can pose a problem because you're not going to get the correct measurement. And also, as a side note, I'll have you know that some years ago I actually did it in both in one particular application because it looked like it was not being done in the other location, so I did it. And then I found out that it actually was being done, so I undid it. Okay, so we ended up correct, but you can sometimes stumble into something because it's a setup for you. So with that, I'm going to pass this along to Ned and Roy, and they're going to be talking to you a little bit about some of the subtleties.
All right, David, thank you very much for a good overview on flow, and appreciate everybody out there spending your day, your lunch hour with us. This is David's slide from just a couple ones back, and we're going to focus now on just the transmitter itself. So we're going to talk about really your number one response is that you're saying the square root extraction takes place in the transmitter. So we're actually going to demonstrate that today. Let's see if I can get this to, there we go. So, and here's Dave's graph again, and I put his quote there, double the flow, 4 times the differential. So, this is kind of difficult to explain, and I just want to make sure everybody out there that we're on the same page here. So if we look at the mathematics, we're saying that the flow output, or in the case of a transmitter, the milliamp output, if you square that, that would relate to the input level or the differential pressure. So if you're running at a 50% flow rate or getting 12 milliamps out of your transmitter, that means that the input differential pressure is at 25% of range. So I'm trying to show the math below here. So if you square 0.5, 50%, you end up with 0.25, or the 25% of the differential pressure. So just maybe this is another way to look at it in the way Dave explained it. And so I took the output. So this column is your flow rate. So as you go really at low flow and then it starts picking up, I went in 10% increments. Here's the equivalent milliamps for that output. But then with the square root going on, here is the DP pressure, the input pressure to generate that kind of flow output. And on my previous graph, we were looking at a 25% input range on the flow, or on the pressure, the differential pressure, gives you your 12 milliamps, and see where this is on the graph. So here we are. I flipped Dave's graph around, but we're sitting here at 25% of the input pressure range is producing 12 milliamps or 50% output. So this is the same graph that Dave showed. But now I want to throw another element here and look at this low range. So a lot of people use the term low flow cutoff. So typically in the DCS, when the meter drops below 5.6 milliamps, which is 10% flow rate, it just assumes that the flow becomes zero. Because look how fast it changes. So as you start at 0, it runs to 5 milliamps, 5.6 milliamps very quickly with just a very small change in pressure. So you can see, as Dave mentioned, just a 1% change in the pressure causes the output to move 10%. So when you're looking at a transmitter, this is very difficult to work with. And if your DCS is cutting this signal off anyway, it's wasted effort to test below this level. So Roy is going to be demonstrating that. So in fact, Roy, if you come in here, let's see if we can show this to the audience.
All right, sure thing. So just so everybody knows what I'm using here, I've got a calibrator and I have a differential pressure transmitter. So I wanted you to see that I'm actually using real gear. I don't have a simulator going on. And once I hit this, now you can actually see my screen. So you should be able to see the MC6 itself. And what I'll do is I'll show you, I will show you, I'm sorry, hello? Yeah, I'm on a webinar right now. I'm on it. Yeah, can I call you back? All right, cosine is adjacent over hypotenuse. All right, I got to go. I love you too. All right, bye. I'm really sorry. That was my mom. What we want to show is the transmitter itself, since it's square root, we want to stay away from the 0. And I have a pressure pump here. Let me go ahead and start adding some pressure. What you might notice that when I'm at 0, let me take it off of a vacuum. When I'm at 0, I'm actually seeing a cutoff. I'm seeing 4 milliamps out. But if I pull this up to what Ned was saying, to just 1% of my input, 1% of 207 inches, which is my span, is 2.07 inches. So if I get close to that, now I'm seeing about 5.6 milliamps, and this is where we want to start the test of our pressure transmitter. And that's the whole point of what Ned is saying here, is that if I go back and not hit this 1%, you're going to see this thing jumping all over the place. And actually, it's even off the graph now. It's jumping around.
Yeah, it's off the screen on the error, so it's just meaningless. And then run it up, Roy, to mid-scale or somewhere around 12 milliamps. So there you're getting a much more reasonable number. And so we just wanted to show, if you've ever done this kind of calibration, you know what we're talking about. It's just all jumpy at the low end. And, the point is you don't want to fail the transmitter when you're testing below 1% of the pressure range, because it's just meaningless data at that point.
True. All right, good. Thank you. So at this point, Sarah, what do we have for questions?
Alrighty, Roy, thanks. Let's start off here. This is the first Q&A session. If you haven't already, if you want to join the discussion and submit your question, you can do so at the right-hand side of your screen. The first question we have here, and please forgive me if I'm not saying your name correctly, is from Ravi Menon. And he asked, this was during David's presentation, can't swirls and turbine meters be eliminated by using flow straightener inserts at the intake?
The answer is yes. What you want coming into a flow meter in general, not only turbine meters, is a good velocity profile. which is no swirl or very minimal swirl with no distortion and things like that. And that can be had a number of different ways. The common way to do it is straight run. That's one way of doing it. If you put in so many diameters of straight run, theoretically, it's gone, okay? However, that's not totally true in some applications, especially in large pipelines where it can actually travel hundreds of diameters downstream. But if you want to be sure, you can use a flow conditioner, flow straightener, and basically take out the swirl, take out the distortion, and things like that. There is a price that you pay because you know, what you see is what you get in some cases, and in this case, the flow straighteners, flow conditioners generally have a pressure drop associated with them, which could be an energy loss for you. So you have that to deal with as well.
All right, thank you, David. We've got another question here, and this question was asked during the magnetic introduction to flow slide. It's from Harold Height. Do the measurements require a full pipe?
Yes, magnetic flow meters do require a full pipe. In fact, all of the flow meters that I mentioned here today require a full pipe. There are flow meters that measure partially full pipes. There are adjustments that can be made on some meters. There are actually a few magnetic flow meters that will measure partially full pipes. They measure the level and they measure the velocity and you figure out what's going on. So, you know, with flow measurement, it's a subject where to every rule there's an exception, so to speak. So that, like I mentioned about the taps being on the top and the bottom of the pipe, there are actually a couple differential pressure flow meters where it is correct to put them on the top and the bottom for specific reasons. Very esoteric, really should, you know, not used very much and should not be used. But it is correct to do it that way for those installations.
Thanks again, David. The next one, well, this isn't a question. It says, Roy, your mom seems nice.
Thank you.
Okay. So next, we have questions flowing in here, so I'm going to try to sort them out. And if we don't get to your question during this session, we'll either hit it at the end or we'll have one of our guys answer it later on after the webinar. So does the type of matter or liquid affect on the flow meter selection?
Absolutely. And that we can talk for a half a day on that. But there are different types of fluids. You've got liquid, gas, and also slurries, and some solids, solids flow, and things like that. That, you know, different meters are more suited to different types of fluids. Also, their physical properties. Are they corrosive? Are they abrasive? You know, for all different types of fluids, there are different types of meters. But yeah, that's you name it. You know, there are certain meters that are more apt to handle certain things and not apt to handle others.
Okay. We've still got about 6 minutes left. Next question. I'm not sure how to word this. According to orifice plate calculus, do you recommend sizing from 1% to 100% of flow? And he means by that not to use DP, by example, 0 to 0.00 inches of H2O.
Right. Let me kind of rephrase it. He's referring to calculations, referring to orifice calculations. And see, I'm going to go off on a little bit of a tangent here, but with an orifice plate, you've got two things that you're dealing with, three or four actually, but let's take the two that are important, the flow element and the flow transmitter. The flow transmitter has its limitations because, as Ned brought out in his little slide there, if you run at 10% of flow, you're only 1% of the differential pressure. So now when you start to get below 10% of flow, or in some cases even more than that, maybe even as much as 30% of flow, you start running into considerable errors on the differential pressure transmitter. The other side of the coin is you also have the flow element that you have to deal with as well. And there are a lot of considerations, one of which is, I hate to mention it because it gets into another discussion, but one of them is Reynolds number and how that flow meter is operating. You need a certain amount of Reynolds number in order to operate properly. And when you start going too low on the flow, you start getting below there, you get inaccuracies there. In order for your flow measurement system to operate properly, you need both the flow element and the flow transmitter operating where it's going to be accurate. Now, just one other point. You mentioned, the questioner mentioned having 100 to 1 turn down, 1 to 100 on the flow. 1 to 100 is 1 to 10,000 on the differential pressure. You will not find a differential pressure transmitter that will do that accurately. You may have to put 2 or even 3 transmitters in parallel in order to be able to measure that if, and this is the thing, if the flow element will even measure at that lower flow. Okay?
Okay. Okay, next question. How does the actual flow affect the distance range from Flowmeter to place a flow conditioner?
Okay. Could you repeat the first part of the sentence again? How does the...
Yes. How does the actual flow affect the distance range from Flowmeter to place a flow conditioner?
Okay. I mentioned this before in one of my answers, and that is that with a flow meter, you want a good velocity profile. And different flow conditioners are put in different places in order to get a good velocity profile at the meter. I had an application some time ago where I had 3 diameters, and that's all I needed for that particular flow conditioner. There are other flow conditioners that might have taken a little bit more. There are others that might have taken, probably not too many, but might have taken a little bit less. You really have to look at talk to the flow conditioner manufacturer and find out how many diameters it needs downstream of it in order to get a good velocity profile. As I mentioned, the one I had was 3 diameters. Yours or different style might be different.
Okay. And how do you deal with low flow in a large pipeline?
That's kind of a toughie, but you know, it depends what you mean by low, and it depends what you mean by large. It's too relative. I don't, you know, it's an issue of turn down of the flow meter, and whether it'll read over 100 to 1 range or a 10 to 1 range or a 3 to 1 range accurately. And the way you can deal with it, one way I mentioned before, is if you have a differential pressure type meter, you can put flow transmitters in parallel. For example, if you had 0 to 100 inches as being 0 to 100% of flow, you can have one transmitter that's 0 to 100 and another one that's 0 to 10. And as a result of that, you should be able to get roughly 10 to 1 turn down. But if you're trying to read very, very small flows in a very, very large pipe, it becomes difficult, and you have to look at the particular technology to see whether it can do that or not. And also, very importantly, what is the accuracy at that low flow, which usually it's not very good, but there are some meters out there where it actually can be, you know, better at low flows than at high flows, but there are very few of those. Go ahead.
Last question for this section. What is the minimum upstream straight length to use if a K factor is not calculated?
Well, okay. That's kind of a nebulous question because I don't know what type of meter it is. And really, let me just say that the upstream and downstream straight run are dependent upon a couple things that are not in the question. One is, what type of meter is it? If it was a Coriolis mass meter, it wouldn't need much of anything. If it was a magnetic flow meter, it would be a few diameters, and I don't want to put a number on it because each manufacturer is different. If it were a vortex shedder, it would be something else. If it were an orifice plate, it would be something else. And also, what does the upstream piping look like? Is it a straight, you know, pipeline that's been running for 1 kilometer straight with no bends, nothing, it's just straight, or is it got some twists and bends and turns in it? So, you know, that would have a bearing on what the straight run should be upstream. So it's, you know, I'm giving you more of the concept. I don't have a particular answer. But I do want to say this. When I was back in the 1900s, when I was learning this stuff, they had, you know, people would say that it was, you know, you need 10 diameters up and 5 diameters down. And that is straight out a myth, okay? It's not really true. Even with an orifice plate, sometimes you need as much as 30 and 40 and 60 diameters upstream and sometimes more. With a Coriolis meter, you usually don't need very much. Just rules of thumb are that's all they are, is rules of thumb. But a lot of times they don't necessarily work well. Go ahead.
Okay, well that's all the time we have for the first Q&A session. Next time, Ned and Roy, we're going to ask that you pipe up a little too.
Oh, right.
Okay, so if we've missed your question during this session, we'll either address it at the end or after the webinar. Katie, what else do you have for us?
All right. Thank you, guys, and thank you, Sarah. As you've noticed, there's quite a few questions, so we thought we'd provide some additional resources for you guys to take a look at even after this webinar is over. The first one is from the ISA bookstore. It is Industrial Flow Measurement, 3rd edition. It is by David Spitzer, and it basically will teach you practical considerations and how to select the best flow meter for your application. And again, you can find that at ISA's bookstore. It's isa.org/books. And we will send you a direct link to it in a follow-up email after this webinar. The second one is by Beamex. It's Ultimate Calibration, 2nd edition. It's 203 pages, and it's basically all you need to know about calibration from basic to advanced. And with that, I'd like to go ahead and hand it back over to Ned to continue the presentation.
All right, Katie, thanks a lot. So now we're going to get down a little bit deeper. We just showed you the noise at the low end, and let's get a little more specific on how we recommend you should test a DP flow transmitter. So, we're all used, if you're a calibration professional, you're used to testing at 0, 25, 50, 75, and 100%. And when everything's linear, you don't even think about it. But remember our slides, and we're dealing with this square root mathematics. So since we're trying to measure flow, it makes sense that you want to focus on the milliamp output. So you really should be testing like at 25% of flow rate, 50% of flow rate, 75 and 100. Also, we brought in this concept of the low flow cutoff. So instead of testing at 0, we're recommending you test at 10% of output. So what we're saying here is test at 5.6 milliamps, then go to 8, then to 12, 16, and 20. So it's a little bit different than what you're used to on a linear transmitter. And I'm having trouble. There we go. So Roy's transmitter that he showed you just a minute ago, its range 0 to 207 inches, kind of an odd inches of water, but that is what matches the orifice plate and the pipe size. And with that, you get 4 to 20 milliamps out, but with square root extraction on the transmitter. So here's what I'm talking about. We're checking at 10%, then 8 milliamps, 12 milliamps, 16 milliamps. So we've backed into, in essence, the pressure required for those test points. So the pressures are very odd with this range of transmitter. But if you dial in these pressures, you're going to be able to see nice, even milliamps. And then finally, when you look at the error, again, people are used to using percent of span. But for flow, we recommend that you use a percent of reading type analysis, not as a percent of span. So just a little bit more about percent of reading. If you were to graph the absolute error in inches of water on a percent of reading type accuracy, notice on how the curve comes down on the square root type transmitter. So we're evaluating the error tighter at low flow and giving more room at the high end by using a percent of reading. So instead of a flat analysis, which would be percent of span across this straight line here, we're saying that we want to be more accurate at the low end. So so to summarize, we're saying that you need to understand the math, that the The differential pressure is going to be the square root of the milliamp range. Consider that there's low flow cutoff going on, and it's really a waste of time, or it's just not good data to test below 10% of the flow or 1% of the pressure range of the transmitter. And it's recommended that you use percent of reading for the flow error evaluation. So again, on Roy's transmitter, I'm going to turn this over to him here, but you're going to see this type of relationship. So it looks kind of odd. You know, we're doing, you know, here's the 10%, here's the 25%, and then 50, 75, and 100. So we're doing a nice spread here, but we're kind of tight down here. But remember, we're looking at, you know, what you're used to, 25%, 50, 75, and 100, and we've added this rule of not bothering with 0. But here's the kind of numbers you might see. So this is real data, real inches of water out to 2 decimal places, real milliamps out to 4 decimal places, and then here's the error that you're seeing graphed here. And then notice this phenomenon at the low end. It's not quite as stable. Things are crossing over here. But in general, this is a very accurate calibrated transmitter at this point. So with that, I'm going to turn it over to Roy and let him show you what I'm talking about.
Yeah, just a minute. Don't turn my video on yet. My camera, what? Hey, just, this is not what it looks like. I am telling you. Let me get my calibrate. Just, I don't want to spill.
Roy, we talked about that.
Yeah, sorry. So, we're going to calibrate a DP, differential pressure transmitter. We wanted to do a 5 up-down test strategy, but just for the sake of time, it's not enough. So, we're doing a 5 up by itself. On the calibrator, my first test point is 1% of my span. So 207, you just move the decimal point 2 places over, and we have 2.07. And let me hit start here. I have a 2-second delay, which is pretty quick. My next test point for 25% is right here in the gray, and I can use my fine-tuning knob if I want to, or I can just, let me just get into the gray area. Look on the bottom right. That's where I'm supposed to be. So now for 12 milliamp output, and so the flow output, because we're calibrating the transmitter itself, we have to deal with the output of the transmitter, which is 4 to 20 milliamps. So I've converted my, I actually jumped past it too quick. Let me go ahead and vent this and approach it again from the bottom. I don't want to vent down onto it. Let me just back down. Here we go. Otherwise, I'll erase any hysteresis that was in there. So I'll approach it from the bottom. Grab my next test point. So this is 50% output. Next, if you look at the bottom right, I need to supply 116.44 inches of water in to get 16 milliamps out. And I've got a gray bar here that says that I don't have to get it exactly because the calibrator is calculating what that output is against that current input. So I don't have to nail it exactly. I'll let the calibrator do the work for me. I've told the calibrator that this transmitter is set to square root, so it's using that curve. And we can see that our very first test point, our 0, is out. I have a 0.25% of reading error tolerance. This thing failed, and I'll use the mouse so you can see where I'm clicking on, but you know that I'm using an actual calibrator. And your calibrator might be a different color as well. As long as it can do a calculation of that input and a square root calculation against the output, then you can do this test. I can put in notes here, so let me put notes. You know what? I'm not going to put a note here on this as found. Here's my graph. The blue lines represent the tolerance. So the 0 across the middle is perfect, and we can see that our very first test point failed. I want to see the numbers. Okay, here we go. My very first one was 0.306% of reading out. Everything else was in tolerance, but I need to do an adjustment. Now, as a tech, do I delete this and trim it and not tell anyone? No. You want to save this as ugly as it is because this will give you trending information. So let me save this. I want to save it as found. Now, I'm back to the beginning. Let me vent off my pressure pump, and I need to hit the secret button. There's a secret button on this calibrator, and it's right here in the top left, and don't tell anybody. Secret button, start communicator. It actually has an official name, which is menu button, but I like secret button way better. We're starting the HART communicator. This is a HART transmitter. If this were field bus or Profibus, it would be exactly the same thing. Just start the communicator, because we can't do an adjustment with, well, a screwdriver or a crescent wrench. If it's a smart device, we have to fire up the communicator and do the adjustments that way. So this does take a little bit of time to connect, and it always takes longer when people are watching you. I don't know why that is. So here it is. Let me click online, and this was it is a Rosemont 3051C, so that'll be under Service Tools. Then I want Maintenance, and if your transmitter is a different color, this menu structure will be different also. So here's Analog Calibration. That's the digital to analog adjustment on the output of the transmitter. What I want to do is to look at the input side, so we'll go to Pressure Calibration, and you see upper, lower, and zero. Zero we don't want to do here. Zero is what you do when you install the transmitter. But I want to run the lower method. I always run the lower first and then the upper. Warning, loop should be removed from automatic control. It is. It's sitting on my desk, so it's not being controlled. Select pressure units. I am using inches of water in. So it says apply low pressure. And I know that I want my first adjustment to be at 2.07. So I'm setting the pump down on a desk so I don't have any additional jiggling of the pressure hose. I've went above it just a little bit. Let's see if it'll come down. All right, I do need to fine tune it to pull it down. So I'm going to leave it at 207 here. I'll hit check. It is stable. And now I'll tell it by pressing this button. It'll copy this page here, paste it up here. So I'm telling it I have an input of 2.07, so it should, you just saw it, it trimmed my output to be 5.6 milliamps. I'm going to remove pressure. Let me hit check. Lower trim succeeded. I need to wait for it to give me control back. Let me hit check again. Now, the red letters across the top means that the microprocessor inside the transmitter is finishing up its job, so I can't do anything until it gives me control back. And I know that I'll have control back once those red letters are gone. So while I'm waiting for that to give me control back, let me just remind everybody, August 18th, Houston, NASA Space Center. All right, it gave me control back. I hope to see some more of you there. If you're lucky enough, you can have Ned and myself as tour guides throughout NASA. I did some checking and I found out where they keep the spare key of the space shuttle. So maybe we can take it around the block. We need to go to upper. Let me hit check. So to back up a second, we're adjusting the lower range of this transmitter and the upper range. We're adjusting these individually. So I just trimmed the lower, and now we need to make an adjustment on the upper so we have this range of 0 to 207 inches. Let me hit check here. So now it says apply pressure, and I'll hit check, fine. And let me take this up to 207. Should I make it look like this is more difficult, or just, no? Okay. So we're coming up. I can do the rest of it through the fine-tune knob. And again, let me just set this down because I don't want my hands to shake or move the pressure hose to have an adverse effect. So I'm letting it sit here. It's coming down a little bit, and I'm watching this. It'll take a little bit to stabilize, and I may even rush this just because of the sake of time. But let me just pull it up again here. And I know that I've already tested this. If I let it sit there for a minute or maybe even a couple minutes, that it'll sit rock solid and I won't have to worry about the pressure falling. But you know the deal if you're in a hurry. So I'm going to force it right here. So grab this, tell it I'm putting in 207. You should watch the output. So it was 20.03 and now it's readjusted itself to 20 milliamps. We're pretty darn close. So it says remove pressure. Let me hit check. Upper trim succeeded. Now it's finishing up the processing on the transmitter itself, and now it's done. Wow, that was quick. So let me hit X. What have we done? We've just done a lower trim at our 2.07 and our upper trim at 207. So now we should see, you can see our test point right now on the right side. Our span on the top is actually great. Let me just vent the pump. And before I hit start, you can see it's jumping all over the place. And that's part of why we don't even try anything lower than 1% on the input. So I'll close the vent on my pump. And let me take this up to 2.07 as a starting point. And do I have to get it exactly on 2.07? No, because we're calculating the output against right now 2.17 or 2.18. So we don't have to get it exact. It'll calculate. Let me hit start. And I have a 2-second delay. All right, I've already grabbed that one. Now I'll put it in the next one. So what's our next test point? How do we know? The bottom right says 12.94. So I'm looking for 12.94 inches of water. And I'm going to not get it exact. All right, I went over a little bit, but I'm still in that gray bar, which is 4% of our target. And we're calculating what our output is. So now we're 8 milliamps out. I'll take it up to 51.75. And I'm just going to get it close. All right, next one. Traditionally, this would be 75% on the input and 75 on the output if it were a linear calculation. So as a reminder, we're doing a trim on this transmitter, and I'm not getting it exactly on 207 because I don't have to. I'll get it close. I'll let it do the math. What do I have? Passed. My largest error was negative 0.028% of reading, which is 11% of our full target allowed. 11% of our 0.25%. Go down. So the notes, I'm just going to put in a note that I'm going to say trimmed. And wait, no, I'm not done yet. Let me hit enter, trimmed. I want a dash. Dash. It's always when you're in a hurry you can't find it. So this is the technician putting this in. This is not me. Okay, so this is the note that will appear on the calibration certificate. And remember, I did not put that. That was the technician. Here's how we left it. And the numbers. So we don't have to type this down as long as you have a documenting calibrator. That's the whole key. Let me hit save, and I'll save it as left. Now, I'm actually done, but let me hit the back button and show you the before and the after. Let me go down to the results. This is how we left it, but if I want to see what it looked like before, let me do show older result. This is the very first result. I'll go back up to the secret button, show newer result. That's how we left it. One more time. Here's how we found it, and there's how we left it. So this, I've just done this really quick. This is how you calibrate a pressure transmitter. But David is going to show you coming up that this is not all there is to flow issues. There might be other items in the process that can affect it, and David will show you that, but I'm just showing you how to calibrate the transmitter itself. So with that, I'm going to hand it off.
Okay. Okay, very good. Thank you, Roy. Let me continue on here, and again, I apologize that I'm repeating myself, but and I'm going to read to some degree. My apologies there, but the accuracy of a flow measurement, and it should be system here. It should be a flow measurement system is based on the entire flow measurement system, which includes the straight run, flow element, and the transmitter. All of these things have to be operating properly and done properly in order for the system to operate properly. And now the flow measurement system, think about that for a second. If you want to calibrate the entire flow measurement system, you should be calibrating the entire measurement system. Okay, so a calibration really is a calibration of the entire system. The problem, you can't take a liter per minute, or if you're in the United States, a gallon per minute of liquid or gas, and put it in your pocket, take it out to the field, throw it through the flow meter, and check and see that the flow meter read 1 liter per minute. Flow measurement is a dynamic measurement. It's not a static one like pressure, temperature, or level. It's dynamic. It's in liters per minute, cubic feet per minute, what gallons per minute, whatever it is. There's time and there's a mass or a volume associated with it. So that's why flow measurement can become a bit of a problem. I have a question for you here. You can just answer yes or no, no right or wrong on this. Do you know what a flow laboratory is? And basically, as you're answering, I'll kind of talk to that, and that a flow laboratory is a facility where the flow laboratory is able to measure the flow going through a meter under test, the meter that you want to know if it's okay or not. That it measures the flow going through that meter very accurately. When you're talking very accurately, it might be 0.05%, 0.1%. Okay, so 2/3 of you know what a flow, or at least know what a flow laboratory is. That's good. That's great. A lot of people, I'm not picking on the 37% here, but a lot of people out there in the industry, have never heard of that before. So having said that, here's a kind of a schematic of a quote-unquote simple flow laboratory for water. I don't want to get into gases. It gets really esoteric when you get into that. But what you have here is you have a water tank, pretty good size usually, and basically a pump. And the pump flows up through a meter under test, sometimes called the MUT, the M-U-T. It goes up through the meter under test, comes over around the top, and goes down into a diverter valve, which then recycles it back into the water tank. And you say, hey, what are we going to do with that? Well, what you're doing is you're basically setting up a constant flow rate going into the meter under test. So if it's 100 liters a minute, you'll have 100 liters a minute, being circulated around in this circle. And then at time, I'll say t equals 0, this diverter valve will be shifted over into this weigh tank. And then instead of the flow coming back into the water tank, it'll be moved over into the weigh tank. Now these load cells are very carefully selected, very carefully controlled, etc., very accurate. And basically the water comes in here and fills up or partially fills the tank. And then after some period of time, the diverter valve flips back in the other direction and continues to recirculate the water. So what you have here is basically in this case, about 100 liters a minute going through the meter under test at all times. Sometimes it's coming here into the water tank. Sometimes it's going into the weigh tank. Now, if you look at the amount of time that was spent diverted, and you look at the actual volume or weight, depending upon the type of meter you're dealing with, what's in the weigh tank, you then can calculate what the flow rate was over that period of time through the meter, and you can compare it with the meter output. So let's say, for example, that it's not going to be exactly 100 liters a minute, but let's say there really was that this meter under test measured 100 liters a minute, and you were running for 6 minutes, so you might have 603 liters, for example, in the weigh tank. Now, you're off by 3. You can figure out what the error is and figure out how close you are to the real thing. And you can also come back and adjust this meter so that it reads reads 603 instead of 600 over that period of time. So this is a flow laboratory. It's usually now there are small ones, but usually they're pretty good size affairs. There's a lot of metrology issues associated with the load cells and especially the diverter valve. And a lot of things to look at here, but also it's relatively expensive from a meter production point of view. It's relatively expensive to operate these because I just did one run, and if there were 600, it took 6 minutes in my case to fill this. It'll probably take another 6 minutes to empty it, and then you start again. So basically, to get 1 point on 1 meter, you took up maybe 15 minutes of time. If you run a slow flow into here and try to fill up the tank, it can take an hour to fill that thing up. So you end up tying up this facility for quite some time if you try to actually run production meters on this. So another approach is to use a flow calibration facility, and this is something that you actually can do in your plant. In this case, you have a master flow meter. Now, I'm going to make up the numbers, but let's say you have a production facility, and I'll take it from that point of view. You're actually fabricating and you're manufacturing flow meters. And so what you can do is you can take this master meter and check it over in a flow laboratory, which we just talked about, and see what it does. Get all its parameters, its K factors, or whatever is involved with that, and then bring it over here, put it in here. And then you can take your production meters as you're actually making them and put it over here and test them out by essentially having a water tank with a pump and flowing water up through the system and around the other side and just going in a circle. Now, at the end of the week, and I'm making up a week, it may be less time, you can take this master meter, recheck it in the flow calibration laboratory, and find out that it is not shifted at all, in which case your production meters can go out the door and get shipped. Okay? Now, how does this thing work? The master meter is basically, okay, it's a master. You set up the flow to be, and I'm going to make up a number of 100 liters a minute. You set it up to be 100 liters a minute in a circle, perhaps with a variable speed drive on the pump, and you look to see that this meter is reading 100 liters a minute. And if it's reading 103 liters a minute, you can make an adjustment to the meter under test to make it read 100, because that's what's really flowing through the system. The advantage of this is that with a variable speed drive, you don't have to manipulate valves, you don't have to play games, you just change the speed and you can actually change the flow. So in just a few minutes, you can get 3, 4, 5, 7 points, 9-point calibrations in a relatively short period of time without having to empty and fill the tanks, as I mentioned before, in the other system. So, this is something that you actually can do in your plant. In our plant, we actually had the water tank in our plant when we had the small one was actually a 55-gallon drum, which in a chemical plant, there are a lot of those around. And we used a drum pump, and we got a master meter, and we kind of set all this stuff up. But I will say that I was not the one that did it, but my predecessor at the plant did. What I did later on was kind of make this a bit more permanent with more piping to it and more real tanks, as opposed to a 55-gallon drum. But this is something that's practical that you actually can do for meters that are under approximately 3 inches in size, to give you an idea. And a question, this is kind of interesting. I'm curious to see what the answer is going to be. I have an idea, but do you have a flow calibration facility in your plant? And like I say, this is something that can be very practical and very useful. We had a case, actually it was my predecessor had the case, which kind of precipitated this, where the plant operators would have a problem, and they would actually tell the instrument people that the problem was in the flow meter at the same time that they were trying to solve their problem. Okay, so they would distract everybody. And as a result of that, yeah, see, that's kind of what I expected, the 80-20 again. About 80% of people don't, maybe 20% do have that. But anyway, what happened was my predecessor had that, and he got tired of sending the technicians out to check things, and they come out okay, and then miraculously the problem goes away. So what he did is he put in this little flow calibration facility. You can go to the next slide there. The little flow calibration facility to kind of handle that, and then after once and twice and 3 times they stopped asking them to go and check the calibrations. I think they went and picked on someone else, but I wasn't there, so it is what it is. Now another way to calibrate systems is a dry calibration. Now, the 2 calibration methods I just mentioned are wet calibrations. You actually put the gas or the liquid through the meter itself. In this one, it's a dry calibration where you verify the physical dimensions, and also you do the electronic stuff that Roy and I guess Roy spoke about it more so, and that as well. And where you check the zero, you check the span, you check up and down and that sort of thing. There might be a scaling factor, there might be an analog output. So these are electronic techniques. And that is another technique that can be used, and most commonly, I guess it is commonly used. So, do we have the next, let me see if I've got it. Ah, there we go. Now, that said, do you inspect your differential pressure flow elements? Now, remember, and again, this is for you guys, so please just put down honestly what you do or don't do. But you remember that I said that the flow elements are important because they're geometrical type devices, and if the geometry changes, you actually change what the meter does. And if you inspect them or don't inspect them, you could have a problem if you don't inspect them. Maybe you do, maybe you don't. Different services are different. There we go. Okay, so about half of you inspect these and half of you don't. And I suspect that the half that do inspect them probably have something to do with custody transfer or some very important measurements. What I've noticed out in the plant is that typically, we did not inspect them. Even though I knew better, we didn't inspect them as long as we had good product and the operation seemed to be stable. We would not inspect them. Now, the types of problems you can have if you go in and inspect, well, there are things you can tell from the outside here. The installation errors, do you have enough straight run? Is it oriented properly? Is the tubing tubed, properly? Is it always sloping in one direction or the other? Is the direction correct? Is there a U? Is there an inverted U? These are all things that you can kind of get from the outside. But on the inside, that's a different issue, and sometimes you can get there and sometimes you can't. In this particular case, I do not know the history of this particular orifice plate. I think we picked this up, a picture off the web, if I'm not mistaken. And so this one here, you notice that this is more like a volcano than it is a plate. And believe me when I tell you that this did not start out as a volcano. It started out as a plate. And probably what happened is it was put into a particular location where the differential pressure across it was so high that it bent it. Or it could be could have been in a location where the, how do I want to say this, where you could have some sort of slug flow where a slug of liquid came along and hit the plate, or there could be, trying to think of steam, where you have liquid droplets of steam condensate coming down the line as well, water hammer, if you will. That was the term I was looking for. Where the liquid is coming down, and it's just like a bowling ball on a bowling pin. It just hits it and hits it and hits it, and eventually it deforms like this. And this meter, aside from being difficult to pull out of the pipe, think about it. It's sandwiched between two flanges, and to pull it out, you actually have to spread the flanges apart in order to get it out. But aside from that, it's not going to measure properly. It's probably going to measure lower than what it would normally read if it were a straight plate. So you're dealing with that sort of thing in that particular case. Now, there are some other, I mentioned at the beginning of the talk that there were a couple pictures that I have, and I want to say that the geometry of the inside of the pipe can also change. And if you take a look at this, if you think this is, I believe it's around a 10-inch pipe, and if you think that this is a 10-inch pipe and you put a flow meter in this line, and then you think the flow meter is going to read correctly, you have another thing coming, or as we say here in New York, I have a bridge to sell you. This is going to pose a definite problem on the flow meter in terms of the cross-sectional area, the diameter of the pipe has just changed drastically. Now, this is caked up. It probably was in water service. Again, I don't know exactly what the service was on this. From what I believe I told this, I believe it was primarily a water treatment company, and they were showing that their chemicals would avoid this type of thing. But I did do some work in a nuclear power plant some time ago, and they had two different flow meter measurements. One was an orifice plate, and the other was ultrasonic. And what I found is they were different. The readings were different by, I believe, around 30%. And by nosing around quite a bit and asking questions and talking to people who had pipes apart, because I couldn't go inside the piping, it was a cooling water line, I couldn't go inside and see what was inside, but I was able to find out that there probably, most likely, was coating, and from the eyeballs of the people that were in there, they could tell me roughly how much it was. And sure enough, when I put in the calculations with a different diameter, I was able to get the two readings to essentially be, close to one another. They're never going to be perfect, but I got them to be somewhat close to one another so that they knew what the flow was through the pipe. Neither of the meters was correct. Both of them were affected by the inside diameter like this of the pipe. So these are things that potential problems. If you don't go in and look, these are the types of things that can occur. Another thing that actually in the plant that I was in, we had sodium chloride brine, and if you've ever seen that with carbon steel pipe, and if you've ever seen the inside of those pipes, they have like boils on them. And when I needed to put in a flow meter, I put in a magnetic flow meter because sodium chloride brine is very conductive. But I also put in a plastic section of pipe that would not have any of the boils over time because I knew that the boils would affect the flow measurement. So, there are things happening inside that you have to think about. And, It is what it is. There's a lot of things to think about. So anyway, kind of summarizing everything here, coming to some conclusions, summarizing, there are things you can do. I mean, the best thing you can do is you can ship the flow meter element and the transmitter to a flow calibration lab. Okay? Problem is, it's expensive, it's cumbersome, you have to pull the thing out, and theoretically, you have to pull out the upstream and the downstream piping as well, or maybe even simulate it at the flow lab, and that it all gets expensive and cumbersome to do. So that's a real problem. The other thing is you can remove and inspect the flow meter element and calibrate them in a flow calibration facility, okay, which is basically with the master meter, okay? And most plants, about half of them here, did not have a flow calibration facility, but it's something that is reasonable to do. And you don't necessarily pull all of your meters out, but you pull out the ones that are important. You don't need everything. Another thing you can do is you can remove and inspect the flow meter element and calibrate the transmitter. So now you're not really looking at the straight run, you're not taking care of it, you're not doing a wet calibration. On the transmitter you're doing a wet calibration, but you're not doing a wet calibration on the flow meter element. But sometimes it can be difficult. I mentioned the legal case where we had 800-pound steam at 800 degrees Fahrenheit, and it hadn't been out in 45 or 50 years. I forget what it was at the time. And had not been calibrated in 7 years, which is more interesting. So you can do that. Or the other thing you can do is just calibrate the differential pressure transmitter. And the thing to understand here is that at best, that is a partial calibration of the flow measurement system. It's not a calibration. People think, oh, I'm going to calibrate the orifice meter. I'm going to calibrate the DP cell. You're calibrating the DP cell, but you're not looking at what the flow meter element is. You're not looking at the pipe inside. You're not looking at a whole bunch of things. But sometimes that's as good as you can do, and so you have to be kind of practical and doing your everyday work. So you just kind of start at the bottom with what you're doing, and then you kind of work your way up for the important meters. Would be a bit more pragmatic. So I believe that is the last slide, and I do thank you, and I believe there are other people that are going to take over for me. So, best.
Guys, thank you, David. That does wrap up our official presentation for today, but we do have one question and answer session left as well. And before I hand it over to Sarah, who will moderate that, I just wanted to tell you about an event that's coming up in November. It is the ISA Process Control and Safety Symposium. It will be in Houston, and the exhibit hall is free, so if you wanted to see the advanced technologies that are out there, visit the exhibit hall. But the symposium itself, there are some great keynote speakers and presentations that you do need to register if you'd like to attend that. And you can go to isa.org/PCS 2016 to do that. And I'd like to go ahead and hand it over to Sarah for the question and answer session.
Thanks, Katie. Okay, we got a lot of great questions, and we're going to try to address as many as possible. So let's start off. Do magnetic flow meters require calibration?
I guess that's mine, and I would say yes. But again, you get into how is it going to be calibrated. There are some simulators that simulate the microvolts on the input, and they basically check the electronics. They are not checking the flow meter element per se. In most cases, there's some that check somewhat. Or you can pull the meter out and put it in a flow laboratory or a flow calibration facility and check it actual web testing. But the calibration should be checked. Just as a side note, some years ago I was involved with a different legal case where the outfall of a paper mill, the magnetic flow meter on there actually took a shift, and I had to go in and kind of sort out what the problems were and get something else in there, that another meter that would actually function properly. It can happen. It does happen all the time.
David, I agree with you. You really can only check the milliamps either using a simulator or just driving it. You can also do like a comparative test. Do you have much? What do you say about like a clamp-on ultrasonic or doing some kind of alternate temporary flow measurement, comparing it against the mag meter?
Yeah, interesting you say that. I'm going to get off on a tangent and come back. But I mentioned about the 800-pound steam, 800 degrees F, and what I did is I actually used other process measurements in chemistry around the process to determine that those flow meters were within a reasonable percentage of what they should have been reading. So if it's impractical, like you have this, I mentioned the 180-inch Venturi. If you have one of those, you can't really bring it into a flow lab because there is no flow lab that'll handle that type of thing. So you kind of look at other things that are happening around, and you use whatever process knowledge you can. And you don't necessarily have to have the process knowledge yourself. Oftentimes you go and you find the person that knows the process, and you basically extract the information out of them because they know the information. They just don't know, they don't know enough to put it together sometimes from a flow meter perspective. And so you can oftentimes actually talk to people and get the answers to those questions as to what's going on, and then come back and look at the flow measurement aspect of it and try to do a material balance or heat balance or both to determine what the flow rate is.
All right.
Okay.
Next, are you finished with your answer?
I'm done.
Okay. Alrighty, what about dead weight testing? Trimming the output is nice, but what about measuring the cell itself? You need to have a reference cell, which the MC106 cannot do. Help? Question mark?
Well, you need to look at the accuracy of your calibrator. A dead weight tester is typically a percent of reading type instrument, but there are a lot of variables. If it's a portable dead weight tester, you need to take into account for specific, or the local gravity. It needs to be level. Are the weights being handled properly? If you're handling weights with your bare hands, I would say a good electronic calibrator is just as good as a portable dead weight tester. But if it's a custody transfer meter, you may want to measure that pressure, with a dead weight tester, depending on the range and accuracy.
All righty. Next question. Roy, did you wash your mug after the last time we saw you drink from it on YouTube?
Seriously? The answer is yes. Yes.
Okay, good. The next real question. How often should the master meter be calibrated?
That one would have to be looked at on a case-by-case basis in the particular application, where it is, how often it's used, and how much it drifts over time. That's really more of a custom. I don't have a rule of thumb for that.
Is there like a number of hours, service hours, or something that?
No, I wouldn't know where to begin on that one. If you've got that, you'll get into it. And the other thing is, but I will mention this: the master meter. There's a question. For example, in a plant, you don't have a flow lab. Okay, you're just not there. What we did, this goes back, and then my predecessor did this, so I don't take credit for it. But what he did was, I believe it was every couple years, he would send that out back to the manufacturer to have it recalibrated, really well. Not just a normal calibration, but really well. Now, keep in mind that the reason he had that there was certainly technical, but it also was political, because everybody agreed that that meter would measure anything, anytime, with absolutely no error. People, they were brainwashed into that, the plant people. So that it was more psychological and more for that than it was for the metrology point of view. Right? Yes, we wanted to do it correctly. That's what he wanted to do. But really, it was to make sure that it was reasonable, and even if it was off by 1%, which is a lot for that type of meter, for a master meter, it didn't really matter because it stopped all the questions and stopped the extra work, and it gave somebody a reference they can get to it, and it may be close, but it's not perfect, but that's okay. And also, every meter that came in the plant, every meter that came in of reasonable size was put on that test stand as well. So we would check out meters before they got installed to know that they were operating properly on the bench.
Right. Can a DP orifice be bidirectional?
I don't know the direct answer to that, but because orifice plates, there are a number of different styles of orifice plates, and the one that's commonly used is the concentric, round concentric orifice plate, and it's beveled on one side and sharp on the other. Now, there are some, if you make them thick enough, they don't have any bevels to them, and so it's really like a hole in the plate, okay, because it's that thick and they're sharp on both sides. So it's likely that you could use them in both directions, and get some accuracy. But orifice plates, even the ones that are not made to be bidirectional, will measure something in both directions. What it measures backwards will be a little bit different than what it measures forward because the geometry is different.
How would you do the vendors on the transmitter would have the zero flow at 12 milliamps, and the mathematics would be crazy going.
Well, either that or they put two transmitters on it, one for one way, one for the other way, or use a split range, as you mentioned, with the 12 being zero, 12 milliamps being zero flow. You really, when you have those type of applications, bidirectional flow, there might be other types of meters that might be more applicable. Magnetic flow meters, for example, will measure in both directions. The ultrasonic meters. The magnetic flow meters, sometimes when you pump up to something, like in sewage applications, you pump up to a tank and then the flow kind of flows back through the line, through the pump, then you get the backwards flow. And if you keep measuring, if you keep totalizing the forward, you'll get a number that, you count stuff twice because it went up, came back down, then went back up again. And so those meters have like net forward flow and things like that, where it subtracts out what comes back the other direction and then pump up again, and only measures at one time. Sorry if I got off on a tangent. Go ahead.
Okay. How do you know if you're dealing with a swirl issue?
Well, strange things tend to happen is basically what it comes down to. You may look at the process, and you might find more water going in than what's coming out, for example. You may find downstream there might be some clue that where you actually see water. I'm picking on water, but you might see water coming out of a pipe, and it looks like more on one side than the other. Swirl is a tough one, and when you have it, and a lot of it's oftentimes difficult to find, to say, oh, this is a swirl issue. Sometimes, sometimes I can look at the piping and say you have swirl, because I know that certain piping arrangements will give you that. Now, the other thing that you can do is there are meters. I'm just trying to think. There was a fellow in the UK that ran a test over in, I believe it was in India, where a pipeline ran over a road and then ran a whole kilometer straight pipe. And what he was able to do was, with the ultrasonic flow meter, he was actually able to look at the velocity profile in the pipe. And what he found was that a few diameters, whether it was 20, 30, 50, whatever it was, a few diameters downstream of where he started the straight run, there was velocity profile distortion, different flows in different parts of the pipe. And when he got down to the end of the pipe, 500 diameters, 2-meter pipe, he got down to the end of the pipe, 500 diameters later, the distortion was just as bad. So, part of it's art, part of it's science is what I'm trying to say. He was shocked when he saw that, and it led him actually, he kind of shared them with me, led him to new conclusions about things that we thought we knew that we really don't know, especially in large pipes.
Dave, a related story, Dave, I think it just reinforces what we've been saying. We have a customer who does custody transfer metering on their gas intake into the plant, which is expensive. And by calibrating, I think they're calibrating like every 2 weeks, but they were able to get rid of that mystery gain or loss that was occurring prior to a better calibration program. And that's going to, if you have this, even if you're doing a good job calibrating, your orifice plates are in good shape and things like that, if there's still a mystery gain or loss, then you need to look at your runs and try to make that kind of improvement and get it down to where you're just spot on all the time.
Yeah. What's interesting, you bring that up, when I started working on that 180-inch Venturi, the water balance was off by about 4.5 or 5%. By the time I got all through, and that was that's the Venturi versus about 100 meters that were down in the valley feeding people in hotels and things like that. And so when I got all done, the water balance was within about 0.5% and then down to 1/4%, which was just totally amazing. And the boss there, who was not an instrument person, he said flat out, he said, that's too good. Undo the last change you made. And so he went and undid the last change, even though I stepped towards it scientifically. I don't just make it read the right number. I mean, I'm with Roy on that one. You just don't put it down and say this is what it is. And so those are the types of things. And that was there were some subtleties on that flow meter and some of the other. There were a few problems down in the valley, but the subtleties on that flow meter were there were just a few of them, and it did affect it quite a bit.
We are out of time for our question and answers. We have about 50 questions left, so guys, you have a lot of work to do afterwards. So before we end, I think, Katie, you have something else for us?
Yes, ma'am, I do. Can y'all hear me loud and clear, I hope? Before we let you go, and once again, thank you all so much for coming, there is another event that's coming up in October 12th, at ISA headquarters in Research Triangle Park, North Carolina. It's more for our managers and executives, and the bottom line here is we're going to talk about how you can improve plant safety and profitability. We're going to have some great experts that will be joining us, such as Peter Martin, VP of Snyder Electric, and Pat Guin, the CEO of ISA. There you'll hear your presentations like, 5 secrets to integrating software systems, and there'll also be some roundtable discussions of how to improve automation systems. And with that, I'd like to hand it over to Sarah to close out for today.
Alrighty, so if you've missed any portion of the webinar, or if you would like to see the recorded version afterwards, we will send you an email with additional links for supporting information. Once we sign off, you will receive an email with a survey. Please take your time filling out that survey. That's how we decide on what subject to address next time. And as always, all good things must come to an end. Thank you for your great questions and participation. We hope you learned something new, and we'll see you again soon.